Welcome back, everyone. Lovely to see you in our slightly new location. One of the joys of today is I can actually see all your faces, including those who I normally miss. So I know there are like 2 or 3 names I've got left, and I'll try and catch you either during lecture or at least after if I haven't already. So we've got some pluses for today. If you remember from last lecture, I announced that we had our final Taylor Swift interaction for the semester, and it's going to be about music analysis. So if any of you have listened to a piece of music before and have wondered I wonder what notes that is in order to play it on the guitar or on the piano, today is for you. We're going to learn about the techniques that you can use as a computer scientist to actually identify the notes in music that you've heard. So our first question that we're going to need to handle is how to actually store the music on a computer. Because once we understand how to store it, then we can understand how to process it. Now let me see if I do have a second microphone. So given that we don't have the roving microphones today, I fortunately always pack some spare microphones. So we'll at least have this. So there are a couple of different things that we could imagine notating down in order to figure out how to store the music. So we could write just the musical notes. We could write like C, D, F sharp, A, G. But when it comes down to it in the real world, the music we listen to is not just those notes. It's those notes produced by different instruments that have different timbres, produce different waves in the air. And those waves are ultimately just vibrating molecules of air, vibrating at different speeds and in different ways. So one thing that we could do to actually notate that down is to measure how fast given molecules are moving in a given span of time. Now, of course, the motion of the molecules is going to vary significantly over smaller and smaller blocks of time, but our human ear is only so sensitive. Just like our eyes can only pick out things of a certain size, our ears can only pick out distinguishing features of those air molecules down to a certain delta T. So beyond a certain variation in molecule speed, we're just not going to be sensitive enough to it. So our goal is to try and encode some of this information in the computer up to the point at which it makes no more sense for the computer to do it anymore because we as humans just won't perceive it. So instead of measuring how fast the molecules are moving, because that doesn't seem like an easy thing to capture, instead what we're going to try and do is measure the amplitude of the wave represented by those particles' motion. So just like you have a wave on the ocean that you could measure by the speed of the individual wave particles moving up and down, and then you draw a picture of the wave, it makes much more sense to try and analyze the motion based on that overall wave picture rather than the motion of the individual molecules. The wave is a stand-in in this instance. So a bit of physics that we need in order to figure out how we should actually represent this from the perspective of computer science. So here is an example of a note that Taylor Swift might have played. Now, does anyone have an idea what this might sound like if you were to actually play this? Anyone done any music before? No one has a musical background? Yeah, Rex. And so what does that sound like? Does it sound like music? Okay, I will play for you on my phone what that might sound like. Here we go. So not particularly musical, but at least it's a starting point for us. It's just a pitch. But our goal is to figure out which particular pitch this is, given the different pieces of information we have about the wave. So instead of storing the whole wave, because that's going to be tricky, we can store elements of the wave at different points in time. So we can store, for example, how much power we experienced on our meter at a given point in time of measurement. Yes, Jack?
How do we differentiate between the different notes that are the same pitch in different octaves?
So that we'll get to in almost the very last slide of today's lecture. So we're going to start working up from a basic sine wave, and eventually we'll have a very short discussion about how to use that to actually do music analysis. Sebastian, do you have anything you want to say?
No, I'm good.
It's good, okay. So just like Jack was saying, a musical wave isn't going to look like just that one note. we're going to have a whole bunch of frequencies mashed together in something that looks a little bit more like music. And those notes might indeed be at different octaves. So you might have the same note that sounds the same to us in our tonal scale, but that's at different kind of registers, different pitches. Or how should I say that? Different multiples of the same pitch. So for example, I could sing the same note low, like ah, or I could sing it high, ah. Well, that's all the singing you're getting. But we want to be able to distinguish which of these two it is. So what we just saw looks like a mix of different waves, and so we're going to need to come up with a way to not only represent this music, but then to split it up back into its different components. And very different amplitudes of all the different waves that make it up. So there's, you can see one of the waves that made it up had like very large spacing between them, and another had very small spacing between them. So we're going to have to represent all of these frequencies as numbers. Now we've got a problem. Most of the numbers that we've been using so far in the class are integers. We know how integers work. We know how to represent them. We talked very early in week 2 about integer bit representations, but we don't yet know how to do this for floating point numbers. So there are a few things that we want out of our numbers that we're representing on the computer, and we'll make up these desiderata. So when we do maths, it should be correct. Our numbers aren't going to be much use if they're not correct. We want the way we store the numbers to be efficient, both for doing our operations like addition and subtraction. We want those to actually be good to implement in circuitry. And we want it also to be efficient in terms of memory. We don't want to take up too much memory just to store a single number. We want it to be easy to write code for, both the code that actually stores the numbers in the first place, as well as the code that uses them. Ideally, we'd like them to be predictable in the way that the storage works. And then able to represent both big numbers and small numbers seems like something we'd want, although not as important as the first thing. And then able to be as precise as we want. So how many significant figures or how many decimal places you might want in your number, we might want that to scale. But all of these are quite complex properties, and we might end up, like we've had to do with the rest of semester, making some trade-offs between some of these different properties at different points in time. So I guess I gave away some of it there. But Sebastian, given that you've got the microphone right in front of you, actually no, you've had too much chance to talk this semester. I need someone new. In the corner there, what's your name?
Zane.
Zin.
Zane. Z-A-N-E.
Zane. Awesome. Okay, so given that we've got integers, can you think of a way that we might represent a floating point number only using integers? So a floating point number would be like 0.54.
Fractions.
So you could do it using fractions. So give me an example of what you do.
0.5 is 1 divided by 2.
Okay, so we could have two integers and say whatever we're going to store, we'll always store things as a fraction. So you'll have to store 2 integers for every fractional number at least. Okay, any other ideas? How could we store numbers? Gabriel.
We could probably use like scientific notation to store the numbers.
Oh, you're getting very far ahead here. Scientific notation might allow us to scale up the numbers. So what we could do is we could use integers and just multiply them by a fixed amount. So say our decimal number, it has 2 significant figures after the decimal place, 0.54. We could multiply that by 100 and get 54. And then we no longer have a floating point number. We've got an integer that we can use. So that's one way of solving the problem. But that has some issues. What might be some issues? Pass the microphone on one. Remind me your name again?
Yeah, Aaron.
Aaron, yeah, that's right. So Aaron, what are some problems that we have if we just say multiply every number by 100 to make sure that it crosses over?
So you said multiply by every integer by that one?
Multiply our floating point numbers by 100 so that they become integers. Will that always work?
Not really.
Why won't it work?
We don't know how much how many numbers are after the decimal point.
Yeah, exactly right. We don't know how much to scale it by. So we have this issue there that our scaling could work, but firstly, it might not be very efficient because we have to do this multiplication every time. And secondly, we don't know how much scaling we're going to have to do in each case. And we don't know how we're going to store that in the first place in order to perform this scaling. Okay, so the next step up might be, well, if you need to figure out how much to scale it by, you could have this scale factor in a second integer. And so we could have one number that contains the significant figures, and then another number that contains how much we scale by. So that seems pretty good. But we can be even cleverer. We can say, let's take all the bits for an integer, and what we can then do is we'll use some of the bits to represent the scaling factor, and some of the bits we'll use to actually represent those significant figures. And this is where we're getting very close to Gabriel's suggestion, where you have a single representation that's going to store all the information you need to scale it to a representation that we know how to use. And this is ultimately Gabriel's suggestion that we took a few more steps to get to. And we're going to follow what's called IEEE 754 floating point standard. And this is just a document that a bunch of scientists agreed on, or a bunch of computer scientists agreed on, to specify how this kind of scaling thing would work. You could imagine a whole bunch of different ways of constructing it that would all work. But what we like to do as computer scientists is come up with standards so that everyone is doing it the same way. So when you take a floating point number from one computer to another computer, the computers will have the same method of doing it, and the compiler authors only have to write how to use floating numbers once. So this is going to be IEEE 754. In the textbook, I'll note that they do something that varies very slightly from this standard, but the way I'm going to teach it here, at least, is only very, very slightly different from the full version in the standard. I'm just going to leave out one or two details, but be aware this is actually different from the presentation in the book in, again, one or two small places. So what we're going to do is we're going to break up our number into a few components. The first will be the sign, whether it's positive or negative, and we're going to need to store that somehow in the number. So who remembers how we store that for integers?
4 bytes.
Do we store the sign in 4 bytes?
1 bit.
1 bit.
Okay, Gabriel, enough from you for the minute. How do we store it? Have you got the microphone as well?
It's here.
Yeah, so you might as well say it into the microphone.
All right. So every integer, it takes 4 bytes to store it.
And how do we know whether it's positive or negative?
There's one more byte.
Do we use a whole byte for that?
Oh no, it's like... actually, I kind of forgot it.
Kind of forgotten. So remember, we use 1 bit at the very end. So if you remember from the early lecture, we had our clocks, and we divided the clock up into 2 halves. And the bit that determines which half of the clock we're in is just that very first most significant bit. So the bit on far one side will tell us if it's set to 0, we're in the positive half. And if it's 1, we're in the negative half. And remember, so we then had all the numbers from 0 all the way from like 0, 0, 0, 0, 0 up to 1, 0, 0, 0, 0, 0, 0, minus 1. And then we had all the numbers from 1, 0, 0, 0, 0, 0, 0 up to 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay, so that's what we're doing with our sign. We'll use 1 bit to store the sign. Then we're going to store all the significant figures in what we call the mantissa. That's just a fancy word to say the significant figures. We're going to then have a base, which is our scaling factor. Just like in scientific notation, you'd normally use a base of 10. And then we'd have an exponent, which is the power of 10 that we scale by. But computers don't use base 10 normally. What do they use? Do you want to pass the microphone to Isaac? What base do we normally use for computers?
Base 2.
Base 2. So for all of our entire floating point discussion, we can just assume that the base is going to be 2. And because we know we're going to use base 2, we don't even need to store it as part of the number. It's just an assumption. Do you remember why we use base 2 in computers?
Because then there's 2 states, like off and on. So
It's 2 states, and what does that mean in terms of actually building a computer?
like there's a 0 or 1. Is that kind of like there's a you either like there is an electrical
It's
connection.
a bit higher level than that. It just means it's easy to construct out of normal circuit components. And so we can very easily create our logic gates. Ooh, careful there, Jerry. Oh, it's not Jerry. What was your name? Sorry? Terry. We still fine? Okay, we're good. No worries. Okay, so now we've got all the different parts of our number, and we just have to figure out, okay, we have, say, 32 bits in which to store all these pieces. Where are we going to store these pieces in each of our bits? So here's an example number that we want to store. We want to store negative 5.432. So we're going to store the significant figures, which are 5432, in the mantissa, and then we are going to store the rest in the base and the exponent. Now you can see this isn't actually the number 5.432 because it's undergoing this scaling. And so we'll talk about how to do this conversion between that representation and the number that it actually represents in normal human form in just a moment. So one other thing is we're going to call this component the scaling factor, the characteristic, even though we can split the characteristic into the exponent value e and the base b. So how many bits should we use for the exponent? How many bits should we use for the mantissa? Does anyone have an idea on this? Maybe pass it back one. I don't remember your name. Marcus. How many bits should we use for each?
I'm not sure.
Well, how would you go about deciding?
I'd say the mantissa should use up more because, I don't know, you don't know how many significant figures you'll need.
And scaling works pretty rapidly, right? So like 10 to the 10 is really, really big. So if we only store the numbers between 0 and 10, then we can go pretty far. But for base 2, that's a little slower. So what would you say is like a normalish range of powers of 2 that you might want to represent?
I don't know.
I mean, you use computers, you use numbers. So if you're doing financial maths, like what's a big number in financial maths?
I don't do financial math.
In finance, like what's a big company? How much does a big company make?
Billions, trillions.
Billions, billions, trillions. Okay, so we probably want to be able to represent numbers up to the trillions. So we're talking like 2 to the 10. Do you know how much that is?
No.
1024. So we probably need to be able to store more than 10 in our exponent, but probably less than, say, 2 to the 500, because that number is getting absurdly large. That's more than all the atoms in the universe. So that's going to give us a bit of a hint. And then what we're going to do is we'll just decide as a standards body, so all of you are going to get one vote, how many bits we should use for each of these. But you're right that the mantissa is going to contain the detailed information about all the significant figures, and so we're going to want to dedicate more bits to that. So this is what the standards organization actually came up with. We're going to store 24 bits in the mantissa in a 32-bit float, and we're going to store 53 bits in a mantissa for a 64-bit double. And this gives you a sense of how much we're going to use. Yes, Jack?
If we've got that extra space in the, like, you're only using 24 out of 32, what's the point of not just going that extra way and using the rest of the 32?
Well, what else do we need to store?
What, did you say you've already reserved that memory though?
So you have 32 bits, and you need to store all of these things, except the base, because we're just going to assume that we know what the base is. So in those 32 bits, you also want to store the exponent, and you also want to store the sign. Sign's only going to take up 1 bit, so we have 31 bits to play with. And then we could use 24 bits for the mantissa and the remainder for the exponent. Make sense? The double here is assuming we have 64-bit integers. Who's got the Marcus? Do you want to get that over to Rex over there?
When you store the exponent, does one of those bits count for the sign of the exponent?
So we just have a specialized bit that is for the sign. So you don't store it in the exponent itself.
But okay, so is the sign bit for the sign of the overall number, like if it's overall positive or negative? But then what if it's to a negative power?
We'll talk about that soon. We will get to that. Okay, so what is our technique for storing this overall? So we've talked about which bits we're going to use for what. Now we actually need to talk about how we use those bits. So the technique for figuring out how to do this is first write out all the significant figures in binary. Then, and we'll discuss how we do that for a number that has a decimal point. Next, what you're going to do is you're going to normalize it so that there's only one significant figure after the decimal place. So just like in scientific notation, you have one number and then the decimal point, and then times 10 to the whatever. We're going to want to have one number times one number, then the decimal point, then the rest of the significant figures times 2 to the power of whatever. You want to encode the significant figures directly as the mantissa, put the overall sign of the number in the exponent there, and then, this is what Rex was asking about, for the exponent, we're going to have a special encoding scheme that we use to determine whether the exponent is positive or negative. So the way we do this is we agree on a bias. And this is going to determine if there are, say, 256 places for 256 possible numbers for the exponent. We'll have half of those be positive and half of those negative. So we'll have 128 and 128 on either side. So positive numbers and negative numbers are all, I guess I've excluded 0 there, but you get the idea. And so what we'll do is the way we use the bias is we'll say, okay, make 127 the base point. 127 will be equal to 0 when we use it as an exponent. 127 plus 1 will just be positive 1. 127 plus 2 will be positive 2. Likewise, 127 minus 1 will be minus 1. 127 minus 2 will be minus 2 as it goes for the exponent. Covered it? Awesome. Okay. So we're almost to the point where we're ready to actually start doing a demo of it, but I've left out one really, really important step, which is how on earth do we convert the number directly into binary? So we'll do a procedure, and I'll go over the procedure, the steps here, and then we'll actually do it, and I'm only expecting that it'll make sense to you when we actually do the worked example in a moment. But the procedure is as follows. So the final representation for the fractional part is going to be 0 point something, 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 something. It's a fractional number. While not finished, multiply whatever fraction you have by 2. Separate out the leading digit. So if the result of the number is like 1.5, take the 1 and just put it to the side and add that to your final representation. Then what you do is you take the number that's left over. So if it's 1.5, we have the 0.5 left over, and then just repeat the process. So multiply 0.5 by 2, we get 1, take out that 1, and then what we've got left is 0, so everything else that remains is 0. So we get 0.11 would be our representation there. But let's actually do it concretely so that it makes sense. And I will use some help from the audience to do that. Now, Nathan, do you want to pass it back one? Oh, sorry, Marcus, do you want to pass it back one? Oh, no, Rex has got it. Charmaine, how do you, no, yes, no, okay. Next to you on the other side. And your name I do not know either.
Avikna.
Victor?
Avikna.
Vikna?
Avikna, yeah.
Avikna.
Yeah.
Awesome. Okay, so give me a second. And let's see how I can switch to the iPad. Oh. Where did my Apple Pencil go? There we are. There we go. Okay. So let's try our first thing, which is just trying to convert a number that's only fractional. And we're going to start with the number 0.625. So do you remember what the very first step was in converting it?
Was it to multiply by 2?
Multiply by 2. What do I get?
0.
Is there a 0 at the start? Oh, you're starting from that side. Okay.
Yeah. 5. And then 1.25.
Okay, so we get 1.250.
Yeah.
So what do we do next?
You separate out the leading digit.
Separate out the leading digit, so that's the number 1 there. And what we have left is 0.25. Now what do we do?
I can't remember.
Same thing again.
So separate out the 2.
Well, not the separate out. Start the whole process from the beginning.
Oh, right. Okay, so multiply by 2.
Multiply by 2.
And then 0.5.
What's the leading digit?
0.
0. And now what do we do?
Same thing again. So
Same thing again. So we get 0.5
times 2.
multiplied by 2.
So we get 1.
And then the leading digit is just 1.
1, and then we're only left with 0, and so we're done. So the fractional representation of 0.625 is just 101, but we're going to write it that way for the time being, just so we remember when we have to add it as the mantissa to the rest of the fractional number. Okay, let's do another one. Avikna was, right?
Yeah.
Do you want to pass it down one? And remind me your name again?
My name's Michael.
Michael, okay. So Michael, you are going to help us out with 0.175.
So times 2.
Times 2.
3.5. Oh, to over 3. Yeah, 0.35.
Yep.
Yeah.
And what's the leading digit?
3. 0, 0.
0. Okay. Make sure to hold the microphone so that people on the recording will be able to hear you. Okay. Now what do we do?
Times 2 again.
Times 2.
0.7. Take the 0 out.
Okay.
And times 2 again. 1.4.
1.4.
So take 1.
Take the 1. Okay.
Yeah, times 2. 2.8.
Oh, whoops. It should be 0.4. Remember, we have to separate out that 1. So now we just get 0.8. What's the leading digit?
0.
And now what?
Times 2 again.
Yep, what do we do now?
Times 2 again.
Okay, 0.8 times 2.
Yeah. 1.6.
1.6.
1.
And that has a
1.
1. Okay, 0.6.
Times 2. 1.2.
And there's another one. Okay, 0.2.
Times 2. 0.4. Takes the 0.
And it takes a 0. And now what do we do?
Times 2 again.
Uh-oh, we're running it. What problem are we running into?
A loop. Also.
So you'll notice that we have 0.4 here, but we already know the pattern that happens when we get to 0.4. When we have 0.4, we get 0, 1, 1, 0. So we get 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0. And so we could keep representing this going on and on and on. And this is just a feature of numbers, which is when you change the base that a number is written in, you might get a representation that requires you to add recurring digits. And this is also another indication, something deep about numbers, why actually in base 10, even if a number appears to be finite, it actually has an infinite number of zeros. Because depending on the representation in which you choose to represent it, you're going to either see those digits represented or not, but they're still always kind of there. It's inherent in the number. So for our purposes, we're going to be happy to take these digits for the time being, and we could write in more digits if we wanted to fill out the remainder of the mantissa and make our number more and more precise. Okay. So now we are ready for our overall putting together a full IEEE 754 floating point number. Now, do you want to maybe pass it down to, do you want to go? No. Abraham, do you want to do it? Okay, go for it. Okay, so the last one, finally, we've got is 14.5. And we are going to have the sign, the overall sign of the number, the mantissa, which contains the significant figures, and times, and what am I timesing it by, do you remember?
It's the decimal point.
So where it's the scaling factor. So 2 to the power of, and that was just E in there. Okay, so first thing we do was write out the number in binary. So let's first write out 14 in binary.
Right.
So do you remember the technique for that?
I think so.
Okay,
So that
hit me.
is that 1, 1, 0.
So you've jumped right to the answer. It was, I think you were getting it right, but we'll slow it down a little bit and remember how to work it out. So just like with the floating point numbers that we were doing multiply by 2, for whole numbers we're going to divide by 2 and use the remainder as our indicator of what digit to take. So we'll take 14, and divide by 2 equals 7. Remainder is 0. Then 7 divided by 2 is 3. Remainder, Abraham, is there a remainder?
Yeah. 5.
3 times 2 is what?
Oh, 3 times 2 is 6. So remainder 1.
Yeah, remainder 1. So 3 divided by 2 is?
It's 1.
1 remainder?
1.
1? I feel like I'm taking you back to grade 4. And 1 divided by 2?
It's 0.
0.
Remainder 1.
Remainder 1. So then we can read off our digits. 1, 1, 1, 0. So let's write that down. 1, 1, 1, 0. Okay, so that's our first step, is to write the whole part. Now we want to write the 0.5 down. So we're going to do the same process as we just did to do the fractional numbers. So do you remember what that was?
Yeah. So it's 0.5.
Yep.
Times 2.
Times 2.
That'll be 1.0. Yeah.
And so what do we do to figure out its representation?
It's the leading entry, so that's
You take
1.
the 1.
Yeah.
So now over here, we'll write 0.1. Okay, now our next step is to scale it down so that we only have one number before the decimal point. So how many places over do I need to move it?
Just 1.
I only need to move it one place over? So if I move the decimal point one place, then I'll get 111.01.
Oh, so it's 1, 2, 3, 4.
So if I move it 1, 2, 3 decimal points,
Oh, 4. What's that
decimal
one?
places, like watch if I do 3, then I'll get 1 point something, something, something.
okay.
And that's what we're aiming for. So that means E is going to be equivalent to 3. And what we can see is each time we move over one decimal place, what we're doing is dividing it by 2. And so to reverse that, we're going to need to multiply it by 2 later. So 2 times 2 times 2 times 2 is the same as 2 to the power of 3. So that's why we have 3 over there. So this will take us to getting the number 1.1101 times 2 to the 3. Now, is this positive or negative? Is the number that we're dealing with positive or negative?
Positive.
Positive. So is positive 0 or is positive 1? Do you remember?
0.
Okay, so we'll write down a 0 for our sign bit. And we know for our mantissa, we can just encode the bits directly. Now, one thing is because we know that there's always going to be a 1 in the first place, we don't actually have to write that down in our mantissa, right? Unless we're representing the, no. So we're always going to have a 1 in that place. And so we're just going to leave it out. And we'll assume when we reconstruct the number that we have to add that times by 1. It's just a default. So our significant figures then for our mantissa are just these digits over here, 1101. So we're going to write 1101, and then all the other mantissa bits are just going to be 0. And I think there are 15 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15. Okay, we're good there. Now all we have left is figuring out how to encode the number 3. Now, do you remember from a minute ago what I said about how we represent the mix between positive exponents and negative exponents? You want me to switch back to the slide for a second? So as a reminder. So step 5 over there. Jogging your memory? Okay, you ready?
Yeah, I think so.
Okay, so what's the rule for encoding our exponent?
So you have to plus E.
Yeah, well, E is our exponent, that's 3.
Okay.
But we need to add the, it starts with a B.
By bit.
We need to add the bias, right? And make sure to keep your microphone so that people can hear. And what was the bias for a float?
Is that 1?
What was the bias for a float?
To 127.
Over there? Yep, 127.
Yep.
Okay, so we add the bias plus E together. So let's go back to our worked examples. So that is normally our E over here. That's our E. And what was our bias?
127.
So what's 127 plus?
130.
Yep, 130. Is 130 in binary though?
No.
No. So, okay, so we have to do our process again. So how do we turn 130 into binary?
Divide by 2.
Yep. Quick maths.
So that's
Help him out.
65. Yeah.
Remainder. Okay, 65 on 2.
2.5.
32. Remainder.
1.
1. Okay. Now it should get easy. 32 on 2. Come on. Quick maths.
16.
16 remainder 0. 16 on 2.
8.
8 on 2. 4 on 2.
2.
And I'm running out of room here. 2 on 2.
1.
And 1 on 2. Well, no seg fault yet. That's just 0. 0 remainder 1. And now we're over to our 0. So now let's read it off all the way at the end. So we get 0, 1, 0, 0, 0, 0. Let me read off the remainders. I think I'm doing this the wrong way. Let me try that again. We get 1, 0, 0, 0, 0, 0, 1, 0. And then we have our representation. So let's write that in. 0, 0, 1, 0. Have I made a mistake?
No, I'm just asking, in this conversion set, we never take 0 divided by 2.
We do, then, yeah, 0 divided by 2. We don't need to do 0 divided by 2, I think. 1, 2, 3, 4, 5, 6, 7, 8. I think that's correct. Yeah. So we've got it right, and now we have, thanks to Abraham, converted our entire number. So it's a bit of an exhausting step to do this for a full 32-bit number by hand. Takes a little while, but it is probably a skill that is worth having for any assessments that you might have. I'm not guaranteeing there will be a question, but it's certainly a question that's been asked in the past, is doing something like this. But we also do take the liberty to tell you, okay, use X number of bits for the mantissa, this many bits for the exponent, etc., to try and reduce the time that it takes. But hopefully you've all at least had a chance to now see how to do it once. Okay. So let me just put it up. Here is an example I prepared earlier, and let me double check that we got that right. Yes, that looks correct to me. And you can see how we did that conversion. What we did is we encoded the exponent with the bias like we just did, so that's 130 there. We have a positive number, so we get a 0 in the exponent's place, and then we wrote the representation of 14.5 as a binary number over there, but we dropped that first one because the first one is always implicit. So we just get 1101. And I know that's a little hard to read on there. Yeah, and what was your name again? Elliot. So Elliot and Isaac, wherever you are, both have very similar long hair. Straight and curly, that's the way I can remember it.
So we dropped the leading one to always 1. So it can't be 0 because actually you're moving it such that you're moving it until you have a 1 in front of the decimal point.
Yeah.
So the only way it would be 0 is if the entire number was 0.
Exactly.
Yeah.
20.5? I'm not going to work out the example now, but you can do it. Yeah, convert it to binary. Yep, Finn? So the bias was just to allow us to have both positive exponents and negative exponents. So we said, okay, let's assume that we have 256 bits worth of number to go around. We're going to split that up so that half of those are positive, half of those are negative. Now you could ask, why did we choose this particular bias way of representing it rather than like our two complements representation that we use for integers? Different people were deciding how to do it, is the answer. There might actually be a better answer, honestly thinking, but I don't know what it was. You'd have to look into the standards documents about why they made that particular decision. Isaac.
Sorry, so you said the digit before the decimal place is always a 1.
That one there, yeah.
Why do we bother storing it?
We don't store it. So if you look here, we've only stored 1101. So we've stored 1101. We haven't bothered storing that first one, just like we didn't bother storing the 2. So that saves us 1 bit there. Now you also probably are starting to get a sense why floating point numbers are inaccurate. Because we're doing this scaling thing and we're only storing so many significant bits, at some point your scaling is going to get thrown off if the number of bits that you need to represent the precision of a number is more than what you have available. So after this scaling property, if you start multiplying it by 2 every time and you've run out of bits for your necessary precision, you're going to start getting the wrong answer. Okay, so we're finally down to our last operators in C, which are tied to what we've just seen. So here are all the remaining operators in C that we're going to cover in the class. And we're also going to talk about some more integer and floating point types that you can use in your code if you want to. So along with our normal integers and our normal floats, we also have unsigned versions of them. And what this means is don't bother about using any bits to store the negative part, because I'm telling you in advance that I only want to store a positive number. And so this allows us to save that extra 1 bit in the case of our integers as well, which actually gives us a ×2 factor increase in the number of numbers we can store. So for example, in our example for the space where we had room for 256 numbers, and we had up to positive 127 and negative 127. Now we can actually, if we say, well, we don't need the negative ones, we can go all the way from 0 to 255. Because remember, 0 is itself a number, so that uses one of the possible slots. And so if you use these unsigned, that gives you that additional flexibility to use that bit. Now, why might you use it? Well, this, in particular in the context of a computer's memory, if you think about using malloc, and how much memory we want to be able to use in our computer, there's no such thing as like a negative memory address. And we want to be able to talk about as many possible memory addresses as we can, because that's going to put a cap on how much physical memory we can actually put in the computer. Because if your numbers only for addresses only go up to 256, then you could only put 256 addresses worth of RAM inside your computer. So we'd like to use as much as possible, and so we use that extra bit and use these unsigned types for things like memory, so to enable us to do more with our hardware. Now we also have a bunch more numeric operators, and these are our bitwise operators. So what they do is they operate on the binary representation of a number. And we'll go through them one by one. We've got shift left, shift right, and, or, XOR, and not. We've still got a little bit of time. Okay, so let's work with 8-bit numbers for the time being, just to save us a little bit of hassle. I don't want to write out a whole 32-bit example every time. So for the purpose of this, we're going to use a type which has a maximum of 8 bits. So when you run out of 8 bits, there are no more bits there left for you to use. So let's represent the number 7. And I am taking this example from a slide I saw on the internet, the particular numbers, just so that we're clear on that. So how do I represent the number 7 in binary? So that is 111. And if I have an 8-bit number, what was it, Chen? Were you the one who just answered? No, who was it that said 111? Suraj, right? Sujay. Close. Okay, who's got the microphone? Thanks, Abraham. Just a few letters off. Okay. This is probably a little hard to see, so let's zoom in a bit there. What am I missing now? I said 8-bit integers.
So you're missing like the sign bit? Oh, like the other 5 bits?
Yep. So 1, 2, 3, 4, 5. So I'm just going to write some slots in just so we can count them. And let's say this is what we call the most significant bit. And we'll call this one the least significant bit. And we can also call that the LSB and the MSB. Now, for our purposes, let's use unsigned integers. So that last bit is going to be part of the number as well. And so let's label these from 0, 1, 2, 3, 4, 5, 6, 7. That's just the number slot of the bit. It's for our purposes just to help me talk about them. Okay, so now what I want you to do is to shift all the bits over to the left by 1 and tell me what number we get.
14.
Very good. So let's write that out. So we would now have 1, 1, 1, and we'll put a 0 in when we shift it over so that we're only effectively doing what's the relationship between 7 and 14?
Multiply by 2.
Multiply by 2. So now we're going to write this operator with like those two arrow symbols, and that is going to be our left shift operator. So what we're doing in this case, we're doing a left shift by 1, which was equivalent to a multiply by 2. Okay, now let's do another further shift. Let's shift that. Ooh, don't know what just happened. Let's do a shift by 3. Okay, so shift it by 3 for me.
Like, do you want me to just count, like, say the bits, or?
Yeah, say the bits.
So that would be 0, 1, 1, 1, 0, 0, 0, 0.
And do you know off the top of your head what number that is?
That would be 14 times 8, which I'm not sure. Wait, 112?
Great, 112. So you've been practicing your arithmetic. That will be on the test. Okay, so how did you figure out that it was multiplied by 8?
So it's 2 to the power of whatever.
So we did 3 repeated left shifts, and each left shift is multiplied by 2. So 2 by 2 by 2 equals 2 to the 3 equals 8. So essentially what our left shifts are doing is we're multiplying the number. So it's x, should have used something other than x. It's x times 2 to the power of whatever the left shift was, is what left shift is doing. Okay, let's left shift it by 1 more. Actually, let's do this. Okay, now what do I have?
2 to the power of 7. Wait, 2 to the power 120. No, hang on.
So the last bit is how much?
2 to the power of 7, so 128.
Yep, 128.
And then 64. So 192.
So that's giving us 192. And notice if I do a left shift a further 2 times.
Just have 0.
Right? This isn't working anymore. We're not just doing a straight multiply by 2 because we've lost one of our bits off the end here. So you have to be really careful when doing these operations that you're not tossing bits out when you intend to keep them. Now, it can still be valuable to do this operation. There are times where you'll want to do the shift and throw away bits. Just have to know that this is something that will happen. So now, if we do a further right shift by 1, what's that operation going to be equivalent to?
Divided by 2.
Divided by 2. So I'll get 0, 1, 1, 1, 2, 3, 4, 5, 6, 7, 8. Now what do I get?
64 plus 32, so 96.
32. So I get 96. And now you'll notice that we no longer get that 112 back. Even though we've shifted back a place, we've now lost that digit entirely. So these are our left shifts and our right shifts. But we still have some more operations to go. Do you want to pass it over to Chen? Sujay? Thank you very much. Okay, so let's give you some new numbers to work with. 1, 1. And I'll make the other number 0, 1, 0, 0, 0, 1, 1. Okay, so we have some new operations now. So our first operation is going to be the bitwise AND operation. Have you heard of this one before?
No.
Okay, so what bitwise AND is going to do is it's going to take two numbers, write them in, imagine that this is what it's doing in your mind. Of course, the circuitry works a little differently, but it places them on top of one another and then looks for places where both of them have a digit that's 1. And then when both of them have a digit that's 1, it produces a 1. And when that's not the case, it produces a 0. So let's go starting from this place over here. So what do I get?
So we get a 1 because both places have 1.
Both are a 1?
Yeah.
Yep.
And then it's a 1, another
Yep.
1, and 0, 0, 0, 0, 0. Yeah, the rest are all 0.
All zeros.
Yeah.
Okay, so that's our AND operator. Okay, we've got another operator. This is the OR operator, and the way we write it in C is using, so you know what the normal OR operator is those two arrows. So the bitwise OR operator is just going to be a single one of them. So the OR operator will give us a 1 as long as one of the two numbers has a 1 in it at that position. So let's do this for bitwise OR.
Yeah. So we start from left or start from
the right again.
Yes, okay. So it's 1, 1, 0, 1, 1, 1, 1, 1.
There we go. And we can see that because at each point we checked to see are either of those two a 1 or either of those two a 1. In this case, both of those were yes, so they both got 1s. Neither of them were a 1, and so that was 0. One of them, at least one of them was a 1 here, so we got a 1, a 1, a 1, a 1, and a 1. Almost done with you, Chen, don't worry. Okay, now we have our exclusive OR operator. And that's represented by the hat or caret symbol. And what this is it gives you a 1 if one of them is a 1 and only one of them is a 1. So if they're both 1s, that's a 0. If A is 1 and B is 0, then it's 1. If A is 0 and B is 1, it's 1. So you've got to make sure that only one of them has a 1. Okay, let's do this again for exclusive OR. Chen?
Yeah, so we start from 0, 0, 0, 1, 1, 1, 1, 1.
There we go. And those are all our two operand operations. So two operand means they operate on two numbers together. You can imagine, again, putting one number on top of each other and then checking the bits bit by bit by bit by bit. And then finally, we do have one single operand operation, and this is our NOT. So let me get a new page and write it out because we were running out of space. And this operation is written using the tilde symbol. And so what we can do is the way the tilde operation works is it just flips every bit that it encounters. So it's the opposite of every bit. So Chen, can you give it to me, starting from the right?
So that will be 0,
0,
0, 1, 0, 0, 1, 0, 1.
Now, what these operations allow us to do is be incredibly efficient with our storage of memory, but also to do things like cryptography, in which you want to hide the contents of each of the bits of a number. And so you really want to have operations that play at the bit level rather than at the byte level or at the integer level. So these operations are very powerful. They're a little complicated, but it's also really good to know these operations for your future careers, because a lot of coding interviews that I've personally done in jobs that I've interviewed for have used these operations as a way to test your ability with some of the lower level functions of C. So they'll say, okay, write a function for me to convert a number from binary to decimal representation, or decimal representation to binary, or some other fancy thing like tell if the bits in a number are a palindrome. So you can come up with all these fun questions, and they do really get asked them pretty frequently. So we are just about out of time, so I'm going to skip the two demo programs and take us finally back to the Taylor Swift, which is the really important part of our lecture. So now we're just about ready to identify the music, now that we can finally represent it. So what we can do is we can take each of our samples and represent for a given time in evenly spaced times what the amplitude of the wave was at that point. So now that we've done that, we can see that, in fact, this was the note A, which is typically 440 hertz, which means that you will get 440 peaks per second. And that sounds like, I don't quite have perfect pitch, so I'm guessing, almost. That was the first note I picked. So that's what that one sounds like. But of course, we wanted to be able to do this on something a little more complicated. And instead of just counting the peaks by reconstructing the wave, we wanted to decompose this complex wave into all the constituent waves of which it was made up of to figure out not just the individual note, but the chord. And a chord is a combination typically of 3 or more notes that fit together to produce some kind of harmonic sound. So in this case, we get C, E, and G, but how did we do this? We need a very special algorithm that's a little more complicated than we have time to cover in the class, but this is called the fast Fourier transform. And there's a slower version of this that's called the normal Fourier transform, but we want to do what's called a discrete Fourier transform, which means we're going to take a non-continuous function. We're going to take these little chunks that were built up. We're going to run it through our algorithm, and this will tell us the constituent waves that make up the larger wave. And finally, we are able to play whatever Taylor Swift song our heart desires. Thank you very much. I will see you in week 12 for our final week.